In this video, we're going to introduce the concept of magnetic field. The SACE learning outcomes require you to sketch pictorial representations of the magnetic fields for various configurations. People have known about magnetic fields for a very long time. It was discovered that lodestones, when not supported, were always pointing in the same direction due to the magnetic field of Earth, and this property allowed it to be used for navigation purposes. It wasn't until 2 centuries ago that it was discovered magnetism was related to electricity, and they are connected concepts. So all electric currents have a magnetic field associated with them, and all moving electric charges create magnetic fields. So magnetic fields are related to the movement of charge. When charges are stationary or static, there is no magnetic field associated with them, only their electric field. So a magnetic field is a vector representation of the influence around a magnet, and because it's a vector, it has both direction and magnitude. So what we're going to discuss now is the direction, and then move on to the magnitude. So the direction of the field lines goes from the north pole to the south pole. So you can see in this diagram that I've got here, the direction, the arrows, go from north to south. But if we had a situation where the north or south wasn't labelled on the diagram, how do we determine the direction of the field? When we talk about field lines, we talk about the direction of force. So for example, when we're talking about gravity, the field lines of gravity are the direction of the force that is experienced by a mass. So when we've got an apple, for example, in this diagram, the direction is the direction of the force, which is down. When we talk about electric fields, the direction of the field at any point is the direction of the force on a positive test charge. So in that second diagram, we've got a positive test charge, and the direction is from the positive to the negative charges. So it follows the arrow. Now with magnetic fields, it's the same. So the direction of the force is the direction from north to south, and is a force experienced by a north dipole. So you can see if we had a north dipole placed in that field, it would be facing from north to south. When we consider electric fields and finding the direction of that field, we use a positive test charge placed in that field to determine the direction. Now with electric fields, we use a magnetic north dipole, so we can consider this as a small bar magnet or compass needle. Now we can't have a north pole isolated on its own, as they come in pairs, like with a north and a south. So even if we had a bar magnet and we cut it in half, there'll still be a north and a south on each part. This is because magnetic fields form closed loops. Now to investigate the direction of a magnetic field, we place the dipole in the magnetic field, and the needle aligns itself with the field, with the north following the field line direction. So we've talked about the direction of magnetic fields. Now we'll talk about the magnitude or strength of a magnetic field. So pictorially, this is represented by the number of field lines crossing a particular area that is perpendicular to the field. So you can see in the diagrams below that a weak magnetic field has few lines and a stronger field has many lines. In figure 7.5, you can see that circled, there's many lines in that small area, meaning the field is stronger at that point. So I'm going to run through a couple of different configurations of magnets now, and first up is the bar magnet. So you can see in terms of direction, the field lines run from north to south, meaning if north dipole was placed in the direction of the field, it will line up from north to south. You can also see the magnetic fields form closed loops. This is unlike electric fields, where the field lines may run indefinitely, but with magnetic fields they always come back from the north to south direction. You can also see in these examples that the strength of the field is high at either end, and as you get further away from the magnet, the strength of the field is weaker. So on this slide you can see the effect that two bar magnets have on each other. In the top diagram we've got an attractive force. The field lines are going from north to south, and they have a closed loop. In the bottom diagram you can see there's a repulsive force, and we've got a neutral point in the middle between those 2 points. So if we had a north dipole directly in the middle there, there'll be no force acting on it. So now we'll talk about the Earth's magnetic field as our next example. So we can see on that diagram, the bottom diagram, that the direction is from the south pole of the Earth to the north pole. Now this may seem wrong, but the direction, we've got to remember that the direction of a magnetic field is the direction of the force on a north pole of a compass needle placed at that point. So a north pole compass needle will point towards the north pole of Earth. Okay, so we have to recognize that the north pole of a compass needle and the north pole of Earth are two different things. So the north pole of a compass needle is the pole that points to the north pole of Earth, meaning the north pole of Earth is attracting that compass needle. So effectively, this makes the north pole of Earth the south pole of Earth's magnetic field. So we can see this from the diagram, the second diagram on the page. We can also see from this diagram that the field lines are not emanating from the south pole and not finishing directly at that north pole, but they're displaced somewhat. So this is because the location of the Earth's geographic north and south poles are not the same as the locations of the magnetic north and south poles. So now we're going to have a look at a straight carrying conductor, which is a wire with a current running through it. Now the current, when we draw it, when it's directed into the page, is represented by a cross, which you can see on the left diagram, and when it's coming out of the page, it's represented by a distinct dot, which is seen in the right diagram. Now we can remember this by thinking about a flying arrow. So when we've got an arrow and it's flying away from us, we can see the tails at the end, so that looks like a cross. When it's coming towards us, we can see the tip, which is a dot. So that's how we can remember that. So we can also see in the diagram on the left, for example, that the magnetic field lines close to the conductor, they're really close together. So it means the field strength is higher there, and as we go further apart, the field strength is weaker, suggesting that the further away you are from the conductor, the weaker the field is. So we can actually work out the direction of the magnetic field based on the direction of the current in the wire by using something called the right-hand curl rule. So what we do is we grasp the wire in our right hand, we point our thumb in the direction of the current, and the direction that our fingers go is the direction of the magnetic field. So our next example is a current loop. So consider a loop of wire which a current flows. So what we do, we grasp the loop with our thumb in the direction of the current, and our curled fingers indicate the direction of the field. So this is an application of the right hand rule as well. Now this loop doesn't need to be circular, it can be any 2D shape, but we can still use the rule to work it out. And the field through the loop is approximately uniform, so we can see this by the bottom diagram that we've got there. So our next example we're going to look at is a solenoid. So what a solenoid is a continuous wire that is wound around a cylindrical core, and you can see this in the top right. So you can consider it a series of loops that are stacked together. Solenoids are used in the creation of powerful electromagnets. So if we place a metal inside the cylinder, such as iron, the iron will magnetize, and what this does is it intensifies the field strength inside the solenoid, creating a powerful magnet. Now we can control this by turning the current on and off, remembering that the magnetic field would disappear when there is no movement of electric charge, so we have full control all over it. Now we can find the direction of the magnetic field of a solenoid by using the right hand solenoid rule. So what we do, we grasp the solenoid in our right hand, wrap our fingers in the direction of the current, and our outstretched thumb gives us the direction of the north pole of the solenoid and the direction of the magnetic field inside. Now we note that the direction inside is actually from the south to the north. Outside we still have our magnetic loops.